Hi, so in this lesson, I'm going to prove basically that root 2 is an irrational number. So how do we go ahead about this? So I'm going to take the root as an the contradiction method. So let's say if I take that root 2 is an irrational, that's what is we have to prove. I assume that it is a rational number. Now, what does it mean is that if I say that root 2 is a rational number, I can write down this is in the form of p by q. So this can be written as 2 is equals to p square over q square. Now remember that if they are a rational number, it means that p and q doesn't have any common factor, any common factor. So what I do is basically, now if I look at p square is nothing but 2q square. So what I do is, if I look at a simple thing here, I can make q squared the subject, which is equals to p squared over 2. And now if you look at, if I look at p squared as a number, when I divide this by 2, I'm getting the answer as q squared. Now what does it mean is that this p, as you can see, must have some common factor of 2, because like how would you divide if this 2 is getting cancelled with p squared, so that p squared has some factor of 2. Now, as there is a logical reasoning that since this is dividing and you're getting an integer answer, so what does it mean is that p has some factor of 2. So let's say 2 times c. I can write on p is 2 times c. So this is one where c is an integer number. So what I do is now I'm going to put this p equals to 2c out here in this relation, or you could say p equals to 2c, you can put it here. So 2c the whole square equals to 2q square. So you get 4c square is actually q square, 2q square. So you get, if I look at this, this is actually can be cancel out. So when I look at now, q square over 2 is actually c square. Now when you look at this statement, it means that when you're dividing q square by 2, you're getting an integer number. It means that q at least contains some factor of 2. Q contains some factor of 2. Now, since p has some factor of 2, q has got some factor of 2, it means that there is at least one common factor with this assumption that p and q has. So p and q has at least one common factor as 2, since they have some common factor that is clearly violating this rule. So what happened is that this doesn't have any factor, actually is not getting supported by this statement. That is the clear indicator that this is an irrational number. So let's take just as one more example on this type of question. So here are three more examples of the same type of question. I'm going to solve first and second, and hopefully the third one as well. But you can try the third one after you watch this. So prove that there are infinitely many prime numbers. So now when I say prime numbers, firstly you understand that those numbers can be divided by either themselves or by 1. So what happened is that let us say I assume that, let us say there are not infinite numbers, not infinite prime numbers. So when I do that, when there are not infinite prime numbers, it means that if I take, let's say n is a set of numbers, now let's say p1, let's say I just first I take is that, okay, let's say that p1, p2, p1, p2, p3, p4, and so on. These are, and pn, these are limited prime numbers. When I say finite, means I can have those numbers like, fixed up. So when I do that, now let us say I define a number which is let's say p1, p2, p3, p4, and pn times pn plus 1. Now when I divide this number n with, now let's say n by p1, you know that this has factor here, but my remainder is going to be always, remainder will be always 1, whether I divide n by p1, p2, p3, p4, and so on. So since my remainder is coming as 1 and it is not completely divisible, it does mean that n is also a prime number, which is not in this set. If it is not in this set, clearly indicates that, okay, n is also additional prime number. Clearly indicates that this thing that I've taken, let's say there are finite prime numbers that I've took here, is actually going wrong, because this is outside the set and still it is a prime number. So that proves that there are infinite prime numbers. Now let's take one more example here. So let's say log 2 to the base 3, I have to prove that's an irrational number. So let's say I say, okay, log 2 to the base 3 is actually a rational number. So when you take a rational number, it means it is of the form p by q, where p and q does not have any common factors. So it can be written as 2 to the power, so 2 equals to 3 to the power p by q. So actually it is 2 to the power q equals to 3 to the power p. Now you notice here that for any p and q integer values, p and q in integer values, the 3 to the power p will be always even, odd, while 2 to the power q will be always even. So that is an indicator that these two are actually not possible anywhere to be equal for p and q being integers. So that clearly indicates that they are not rational numbers. So this